All right, so what I want to do is go over the calculations for the aerobic fitness case study. The first calculation begins at number 4. And so that question says, calculate the energy cost of each workload for all 3 stages using the ACSM leg ergometry formula from table 4.3. And then I provide you with the formula. So the formula is the workload in kilogram meters divided by the mass in kilograms times 1.8. Plus 3.5 plus 3.5. All right, now keep in mind I tell you that you have to do this for each stage, and there were 3 stages for this particular client. So we'll start here. The workload in kilogram meters, 180 divided by 79.5 times 1.8 plus 3.5 and 3.5 is 7, so we can just do that. All right, and so 180 divided by 79.5 is 2.26 times that 1.8 plus 7, and then 2.26 times 1.8 is 4.07 plus 7, that's going to equal to 11.07. And of course this is in milliliters per kilograms per minute. And I asked you to do this to convert it to METs. And so all you do to convert it to METs is divide by 3.5. And you'll get 3.16 METs. And this is for the first stage only. Now, when you go to the second stage, all of the numbers remain the same with the exception of the W, the workload. And so you use the workload for stage 2, then the workload for stage 3, but you complete the calculation the same way as you did for stage 1 for both stages 2 and 3. All right, so the next question, question 5, says plot the client's heart rate versus workload in METs. You may use graph paper or Excel. So right here, I've already drawn a graph and I've already plotted the client's heart rate versus their workload in METs. Now, in order to get the graph right, you had to get your calculations right in number 4 for each stage. Okay, so there were 3 stages. You had to calculate the energy cost of each workload for each of those stages. Okay, so the numbers that I got for my number 4 is I got 3.16 METs for stage 1, 4.33 METs for stage 2, and 5.49 for stage 3. And the corresponding heart rates for the first stage, it was 119 because you take the last heart rate for that last minute in that stage. The second stage, the last heart rate was 138. And then for the third stage, the last heart rate was 163. So I plotted this here on this particular graph. So 3.16 here on, this is METs down here. So on the x-axis, 3.16 will fall somewhere up in here. And then I went up to 119 on the graph, so I put that point there. The next one was 4.33 33, so that's somewhere in here. And I went up to 138 on the graph, so somewhere in here where I drew the point. And then 5.49 would be somewhere down here. And then 163 on the graph be somewhere up here. All right. And then the next thing that I told you to do after drawing that graph, I said, okay, well, what is the client's VO2 max in METs and milliliters per kilogram using the graphing method? And I tell you how to use the graphing method to come up with the client's VO2 max. I said, well, hey, draw a best fit line through the points. So a best fit line, try to see the line that's equidistant from all the points. If it's able to go through all 3 points, great. So tell you to do that. That's the best fit line. That's my best fit line. All right, then I said, next, draw a horizontal line across the graph that corresponds to the estimated heart rate max, which is 220 minus the individual's age, where our client is 35. So 220 minus 35 is 185. And so that's about right here. So I said, draw a horizontal line across there. Now we have that. Then I said, next, you want to draw a vertical line down from where your best fit line intersects your heart rate max line, all the way down to the x-axis. So this is where they intersect right here. This is the intersection of the best fit line and our heart rate max line. And you want to take your pen and go all the way down to the x-axis, and this is going to give you your estimated max in METs. So your estimated max in METs is about, if 7 is right here and 6 is right here, I'll say about 6.8. About 6.8 for your 6.8 for your estimated max using the graphing method. And I also told you to give it to me in milliliters per kilogram per minute. So the only thing you do is multiply 6.8 times 3.5, all right? And that's going to give you, let's calculate this, 6.8 times 3.5 will give you 23.8 milliliters per kilogram per minute as your estimated max using the graphing method. So the next question says, based on your answer to number 6, which we determined was the client's VO2 max using the graphing method, what is this client's cardiorespiratory fitness classification based on table 4.1 in your textbook? Now, if you go to table 4.1 in your textbook and you go under male and you look for your client who is 35 years old and you look for 23.8, you won't see it on the chart, but you do see a category there that says less than 40 milliliters per kilogram. And so since we determined that its VO2 max based on the graphing method was 23.8, we know that that's less than 40 milliliters per kilogram per minute, then that gives our client a cardiorespiratory fitness classification of poor. His cardiorespiratory fitness classification based on table 4.1 in your textbook is poor. All right, so the next question says, based on the fitness classification in number 7, which we determined to be poor, use the VO2 reserve formula, which equal to the percent intensity times VO2 max minus VO2 at rest plus VO2 at rest, to calculate the client's target MET zone. And I put in parentheses, minimum and maximum. So that's just letting you know that there's going to be a range. You're going to need 2 numbers. So there's 2 calculations that you're going to have to use using the recommended intensity in table 5.1. Now, we just determined that our client's classification is poor. So we go to table 0.1 and we find the poor cardiorespiratory fitness classification, and we see that the range that they have there for exercise intensity is 30% to 45%. All right, so the first thing that we're going to do is do the calculation for the 30% exercise intensity. That's going to give us the minimum as far as that zone that we're trying to come up with, or the range that we're trying to come up with. All right, so exercise intensity, whenever you're doing percents in calculations, you change it to a decimal. So that's going to be 0.30 for the 30%, so 0.30 times VO2 max. Now remember, the VO2 max that we determined using the graphing method was 6.8, because we're working in METs right now. We could have used the 23.8 and everything would have been in milliliters per kilograms per minute, but right now we're going to deal with METs. So we said that the METs for his VO2 max was 6.8. Then minus VO2 at rest. If we're dealing with METs, the VO2 at rest is always going to be 1. All right, so 6.8 minus 1 plus VO2 at rest, which is once again 1. All right, and then we just calculate this out. So 0.30 times 6.8 minus 1 is 5.8 plus 1. All right, then 0.30 times 5.8 will give us 1.74 plus the 1. That gives us 2.74 METs. So this is the minimum of this range for our MET zone. All right, 2.74 is the minimum. And then to do the maximum, we just go back, and instead of using 0.30, we use the upper end of that range, which we determined from the chart, table 5.1. In our textbook, we determined that to be 45. So we would change this 0.30 to 0.45, and we would go through and do the calculation the same way, only we would be using 0.45 instead of 0.30 to get our maximum of the MET zone that we're trying to calculate for this particular question. All right, so we're still working with number 8 calculation. Keep in mind I showed you how to do the minimum for that MET zone and showed you how to go about finding out the maximum for that MET zone. Well, the question goes on and tells us to plot the target MET zone on the graph paper. So we can use the graph that we've already drawn, which is why I left it up here on the chalkboard. And so in my calculations, when I calculated the target MET zone, if you recall, I had 2.74 as my minimum. And then when I went through and worked it out for the 45%, the upper range of the MET zone, I came up with 3.61. And so now I'm going to plot that 2.74 on my board. So 2.74 and what I do, I just plot it on my best fit line. So go 2.74 up to my best fit line. That'll be right about there on my best fit line. And then for that upper range, I came up with 3.61. So this is 2, this is 3, this is 4. So 3.61 would be right about there. All right, so that's, oops, I want to keep it on that best fit line, sorry. 3.6. Right there, okay. And then I just draw a line down from the 3.6. and the 2.74. Then if we go on and read the question, it asks us to, let's see, according to your graph, what is the target exercise heart rate zone? And so the only thing we do here, and remember we said zone, so once again you need a minimum and a maximum. So this is where my first plot dot was for the METs on this best fit line. So we just go across to the heart rate axis, have that right there. Then same thing for the point that we drew for the maximum range, or the maximum of the range for the MET zone. And draw that across. All right, so for this one, that gives us a heart rate, this is 110 right here. So a heart rate of about, I'll say 112 to this heart rate here, about 125. So about 112 to 125. Let me write that where you can understand it a little better. So 112 to 125 is the heart rate zone that we came up with just from plotting our MET on the best fit line. All right, so the minimum MET here, 2.74, corresponded to about 112 beats per minute, so heart rate. And then the 3.61 corresponded to about 125. So our heart rate zone is 112, which is the minimum, to 125 is the maximum for our particular client that we're dealing with in this question. All right, so we're moving on to the next question. Now calculate the percent heart rate reserve using the formula percent heart rate reserve equals to percent exercise intensity times heart rate max minus heart rate at rest plus heart rate at rest. And we're using this formula to identify the target heart rate zone. Once again, you see that word zone. So I need two numbers, a minimum and a maximum. Now in number 8, we determine the target heart rate zone using the graphing method. And now we're going to determine our client's target heart rate zone by using a simple formula. All right, so let's get to it. So as far as the percent exercise intensity, once again, we're still looking at chart 5.1. And that range for the exercise intensity was 30% to 45%. So let's start off with the 30%. Okay, so 0.30 times heart rate max. Now we determined the heart rate max to be 220 minus his age, which was 185, minus heart rate at rest. Now the resting heart rate I gave you in the case study. I said that his resting heart rate was 71. Plus the resting heart rate, once again, 71. All right, so let's go through, do this math. 0.30 times 185 minus 71 gives us 114 plus 71. And then 0.30 times 114 gives us 34.2. Then plus the 71. And we do that math, and we come up with 105.2. So this is the minimum, or you can just say 105, because who's going to look at the decimal when we're talking about heart rate? So we can say 105 beats per minute is our minimum heart rate target zone. And now we need to do the maximum. And with the maximum, you're just going to do 0.45. Right? And for the maximum, we just do 0.45 and go through and do the calculation the way we did it for the minimum. So the next question asks, how do these calculated target heart rates compare to those that you obtain using the heart rate versus MET graphing method? So if you recall from the graphing method, the heart rate that we came up with was 112 to 125 when we graphed out the MET zone and did the corresponding heart rate. And then as far as the calculating the target heart rate zone, we had 105 for the minimum. And if you calculated the maximum using 45 or 0.45 there, then you should have come up with 122. So our range would have been 105 to 122. Right, so 105 to 122, and we want to compare that to 112 to 125, which is relatively close. So using the graphing method versus the calculated method, we come up with a similar range for our target heart rate zone. All right, so our last question: how long will he need to cycle at the minimum exercise intensity in METs in order to expend 100 kilocalories during the aerobic workout? And then I tell you, start by using the formula kilocalories per minute equals to METs times 3.5 times the body weight in kilograms divided by 200. I go on to tell you that when you use this formula, this will give you the number of kilocalories that he burns per minute. And if you know how many kilocalories he burns per minute, then you should be able to use that information to calculate how long your client will need to cycle to burn 100 kilocalories per minute. So let's start with the formula. METs times 3.5 times the body weight in kilograms divided by 200. Now remember, the question asks you about how much time it'll take him if he was exercising at his minimum MET zone, at the minimum portion of his MET zone. Now we determined back in number 4 that the minimum METs for that first stage was 2.74. All right, so you had to do that very first calculation correct in order to get the following calculations correct. So we got 2.74 times 3.5 times his body weight in kilograms, which is 79.5, and divide that all by 200. All right, so 2.74 times 3.5 times 79.5 gives us 762.4, and divide that by 200. All right, and so that gives us 3.81 kilocalories per minute. So this is how many kilocalories that he is burning per minute. And we want to know how long he needs to cycle in order to burn 100 kilocalories per minute. So what we do is we take the 100 kilocalories per minute and divide it by 3.81 kilocalories per minute. And that will give us 26.2 minutes, right? 26.2 minutes. So that's how long he would have to cycle in order to burn 100 kilocalories. All right.